So I'll go over the third problem. Yeah, so this one's kind of hard. It's maybe the hardest one. Um, yeah, I think it's harder to come up with, but algorithm is maybe a bit straightforward. I'll just go over it. So yeah, so there's a factory that can be described as an n by n grid of conveyor belts. So you can either go left, right, up, down, or there's not a conveyor belt yet, right? So maybe the current state of it might look something like this. There's a conveyor belt here, and maybe there's something like this. So you can keep going in a cycle, right? Um, and they define a state to be unusable if when you're starting at the state, you can't leave, right? So for example, like, yeah, so they're just considering you have like these conveyor belts, consider like adding new conveyor belts to it, right? However you want. Um, so a cell is usable if you can leave it, right? So this cell here is usable. If this was also a conveyor belt in the beginning, this cell is also usable. Um, and these cells here are unusable, right? Yeah. Uh, so this problem is related to given a conveyor belt. When you're adding new or given a grid of cells with conveyor belts, when you're adding new conveyor belts, trying to maximize the number of cells from which you can escape the grid, right? Yeah. So the exact problem is like initially the grid is empty, and then at each time step, a new conveyor belt is added, right? Then after each time step, you need to find what's uh, what's the maximum number of places from which I can exit if I add the conveyor belts in a certain way. I guess we can go over this example. Yeah. Oh, okay. Yeah. Um, Wait, I think I flipped something around. Just give me a sec. Uh, oh, okay, yeah. Yeah, I was correct. Yeah. So minimum number of unusable, same thing as maximum number of usable, right? So minimum number of unusable in this case, let's say the conveyor belt is like this. Um, so yeah, um, yeah. So yeah, so these two are unusable. Oh yeah, and then this one is also unusable, right? This one is also unusable because you'll go here and then you'll keep cycling, right? And then for the rest of the cells, you can just do like left arrow here, down, left, right, right, right. So you can escape from all of these cells, right? So the answer is going to be 3 here, right? So let's look at the subtasks, right? Um, so the first subtask is n is up to 10. So maybe some kind of n to the 6th thing. Second one is n is up to 40. And then the last one is no additional constraints, um, right? So let's consider a set like a square with conveyor belts, right? Let's try to do a small case. Um, so let's say we have this thing and it already has its conveyor belts, right? Maybe this one is in a cycle, so you can't escape. Um, and then this one, you also can't escape from it, right? Yeah. Let's say this is the current state, um, right? And then basically how you can think of this is each thing that doesn't have a cell, you can add however you want these conveyor belts, right? So you can either add up, left, right, or down on any of these, right? Right? So then the question is like, if you add all these up, down, left, rights, then from how many cells can you exit the grid, right? And one way to think of this is like, so you can exit the grid if from one of the boundaries you have something like this that points to the left, or points to the up on the top, right? So what you can do, you want to find the number of cells from which you can exit the grid, right? Goal to find number of cells from which you can exit the grid. And you can exit the grid if there's a path to the outside, right? So what you can do is you can do a DFS on the reverse graph. Right? So you can start from all the things in the boundary and then just run a DFS on the reverse graph. And this will give an O of n squared time. It'll give you all the usable cells, max number of usable cells. And then the number of queries is up to like n squared, right? Yeah, number of queries is up to n squared. So then this will be, yeah, this will be O of n to the fourth, right? Any questions about this? So what I'm basically saying is for all the cells that are empty, they have question marks, you can add a conveyor belt however you want. So you can think of these as their edges are pointing up, down, left, and right. And then you want to find the total number of cells from which you can escape the grid. And how you can do this is you can do a DFS on the reverse graph, starting from the boundaries. So then this will be n to the fourth. So that's enough to pass cases 6 and 7. Yeah. So let's talk about the full subtask. So this might yeah, so this is kind of maybe a bit tricky to observe the full subtask. So so let's just consider like what happens at the very end, right? Draw this a bit smaller. So at the very end, you have a bunch of things like this. Yeah. Yeah, so at the very end, the conveyor belt's already filled, and you can do a DFS on the reverse graph uh, to find which cells are usable, right? So maybe I'm just randomly picking. These are not necessarily right, but let's say like red is like usable cells, right? Um, so at the end, what are all the usable cells, right? Um, right? And then you can consider like notice that like if a cell is usable at the end, it must have also been usable beforehand, right? This is just because as you're adding more and more edges, there's fewer and fewer options to exit the grid from each location, right? So because of this, as you reverse the process, there's only going to be more and more usable cells. So the idea is like process backwards. And then let's say, yeah, um, yeah. So if I change this one, uh, it's not going to change anything if it's already unusable. But if I change something here, then I can start another DFS from here. And then maybe, well, once this has in a reverse DFS, then I might visit more things, right? So the idea is process backwards, and then when removing conveyor belt, basically the things that I can reach the boundary from, they're kind of connected in some way. Maybe there's multiple connected pieces, but if something that we change is part of one of these connected pieces, then we can expand. We can expand the usable cells. So removing conveyor belt, do another DFS if it can reach the boundary, right? Um, and yeah, so when you're doing another DFS on the graph, so I can just draw here. So maybe in the beginning, like uh, the usable cells was like here. And then after you remove the first thing, maybe it's expanding here. And then after you remove the next thing, it's going to expand here. And then after you remove the next thing, it's going to expand here. So the sum of these sizes is O of n squared, right? So the sum of the complexities of the DFSs is going to be O of n squared, right? Because yeah, each DFS is going to visit some amount of cells, and then the sum of the number of cells you visit is going to be O of n squared. Yeah, so the time complexity is O of n squared. Yeah. Any questions? I guess I'll summarize this. Yeah. Um, yeah. So this was the problem. The goal was to find the maximum number of cells from which you can exit the grid. Um, and you can kind of view this as a graph problem. The things that we haven't put conveyor belts on, you can think of them as a graph with four edges in all directions. And then we want to see from how many of these can we exit the grid. This is the same as doing a DFS on the reverse graph. Yeah, yeah, yeah. So I can also explain some of the things I tried and failed on problem 3. Yeah, sure. Yeah. Um, so I think one trap, um, I don't know if this was the case for others. Yeah, I guess I'll just complete this. Yeah. So do DFS on reverse graph to see from which cells you can exit. Um, yeah. So I think one trap for me personally was so there's something called a functional graph. Um, so it's basically like each vertex has out degree 1. And I think this kind of graph may have showed up in some silver problems, also in some mock tests. Um, so it has this kind of structure where each component is like a cycle, and then there's a bunch of trees that are in each cycle. So a functional graph might look something like this. Yeah. So yeah, I guess some things that I was trying to think was like if there's a cycle, uh, then like you're trapped inside here. So I think that didn't work. Or like this kind of intuition didn't really help too much. But it doesn't hurt to think about it. Um, yeah. Uh, but I guess for like the um, yeah. So I guess like yeah, it's useful to try to do the small subtasks. Um, uh, yeah. So I guess for like n up to 10 or something. Uh, yeah. So n up to 10. You can do something like you start from each cell and then you do DFS and then see if you reach the outside. So this will be like O of n squared per cell. So then if you multiply this by n squared, this will be O of n to the fourth per query. Yeah, I did think of this when I was doing the contest too, in the beginning. Yeah, but then you can realize that uh, like yeah, I guess you can realize that you can see this as a graph. Um, and then I think the key observation to yeah, so you can see this as a graph. Um, I think one way I tried visualizing it is like the things on the boundary that you can reach the outside with, you can connect it to like a sink node. So it's basically you're trying to see if from each node it's possible to reach the sink node. And it's kind of hard if you start a DFS from each vertex. But if you think of it this way, then if you reverse the edges from the sink node, it's just one DFS to see which vertices you can reach, right? I think the trickiest part was actually finding the like actually doing the last subtask. So I guess one comment about this contest, I think yeah, full solving the first and then full solving the second, and then getting the first two partials, I think that gives 800. So that's probably safe for passing. Yeah. But for the last one, I guess the way I guess I tried a bunch of different things, but one thing that worked is like the key idea is like if something is usable earlier, uh sorry, I guess like um yeah, so if something is unusable earlier, then even after you add edges, it's going to be unusable later. So if it's like usable later, then it'll be usable earlier. Yeah, so I think this is like the key observation that leads to the actual solution, um, where you have to like expand your usable things. Yeah, that's what we ended up doing here. Yeah, but I'd say this is kind of a hard one. Yeah. Um, yeah, and then once you come up with this observation that can lead you to think about which ones are usable, and then try to expand this as you go to earlier queries. Yeah, 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 and I think it's also like somewhat tricky to uh, like convince yourself that this works, uh, but it does work because like you keep the visited, like you like if something is visited, then it's always going to be visited. So the number of new things you visit is going to sum to n squared. Yeah. What do you think will be the cutoff for silver? Um, I can't say because it's not out, but I'll be surprised. I mean, I'll definitely be surprised if it's more than 750. I guess that's all I can say. Uh, oh no. Yeah, great. Thank you. I'll stop my share.